Hello and welcome to the 13th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. So far we have looked at behaviors which are given by kernels of polynomial differential operators, right? We have written our systems to be like this, where this R psi is a polynomial matrix of size G cross Q. Yeah, these polynomial matrices where the xi is understood as the differential operator. This is for continuous systems. We did not do the analysis for discrete systems explicitly, but I have been telling you that similar analysis, almost the same analysis, holds true for discrete systems as well. But when the discrete systems are defined over Z, then you will also have to allow two variables, sigma and sigma inverse, like xi and xi inverse, because there this shift, this sigma being the left shift or the backward shift, this other its inverse also is well defined, unlike the inverse of d dt. Okay. Discrete systems, of course, as I have been telling you, will be something that you will be dealing with in your exercise problems, and in the later part of this course we will work on discrete systems as well. But remember that for us to understand those later parts involving discrete systems, it's very important that you go through the exercises about the discrete systems, the preliminary results of discrete systems, which we have not been proving in the main part of the course, main part of the lecture. Yeah, but giving you as exercise problems. Right. Now, what we are going to do in today's lecture is that we are going to look at a little different representations. We are going to look at different representations of such behaviors. Right. So, once again we will be dealing with ordinary linear differential equations with constant coefficients. For us, this d means either differential or difference. Differential for continuous systems and difference equations for discrete systems. That will still be true, but we will allow variables more than manifest variables. We will allow other variables as well, namely this latent variables. What do we mean by that? Well, you see, remember, I mean, sometimes when we are doing modeling, right? When we are doing modeling when we are modeling a system, for example, this Wheatstone bridge circuit that we have been looking at quite often. Yeah. Pardon my bad drawing. See, the variables that we are actually interested in are these port variables, namely V and I. So, we should ideally write equations involving V and I only, right? This is my W. So, if I want the system's behavior, this W must satisfy some ordinary linear differential equation with constant coefficients, which means I should have some polynomial matrix R d dt acting on this variable pair V I equal to 0, right? That is the ideal situation. But you see, in most cases what we will do is we will assign currents here in these branches of the circuit, and we will also assign voltage drops, and we will use these voltage drops and currents in these branches. I mean, current through the branches, voltage drops across the branches as our extra variables, and that allows us to write the equations in a nice manner, in an easier manner. Likewise, if you remember the speaker circuit, right? In the speaker circuit case, we have this electrical circuit, right? It sets up this armature current. This is the incident signal V. It sets up a current I, and that current is the armature current. That armature current causes a magnetic field. That magnetic field causes this bobbin to move, and this bobbin in turn is connected to the frame through this diaphragm, yeah, and this whole diaphragm and spring system and the frame gives us a spring kind of a mechanism. So, this is the position x, and the idea is that this movement of this x will cause the sound wave, right. That is how the speaker works. So, if you look at the system like a black box kind of a thing, then all we are interested in this incident signal, which is this voltage V, and the x, the movement of this bobbin, yeah. And we are interested in the relationship between V and I, V and x, right. All these other variables are auxiliary variables, yeah, namely this armature current. If you want the vector field that it, sorry, the magnetic field that it sets up, all these variables, if you want them to be there, or the force, for example, force indeed, the force that it creates, the magnetic force, these are variables which are there to help us write the equations, okay. But as such, we are interested in the relationship between V and x only. So, in other words, the manifest behavior involves the manifest variables, that is the variables of our interest. All the other auxiliary variables that are used for the modeling purposes, they will be called the latent variables, but the presence of both these variables are equally important as far as the equations are concerned. So far so good, but the question is, if that is so, then all this analysis that I have done so far needs a reworking, isn't it? Because all the analysis that I have done so far involved only equations like this, right. There was no place for this L. But one might say that, okay, just for the sake of it, take W and L together, right. So, in that case you will have something like, okay, R d dt, another polynomial matrix acting on W and L together, right. This should be treated as the behavior, that is right, this should be treated as a behavior, but the behavior will have both these variables W and L, and such trajectories involving both W and L will come from what is known as the full behavior. This is not the behavior. If you remember, the behavior must actually then be given by B is the collection of all those W's, yeah, coming from, for the continuous case, C infinity, yeah, such that there exists an L which is also a C infinity function of some size. Let me use the letter K, such that together W and L is an element of the full behavior. That means it satisfies the given equation. The question now to ask, the legitimate question to ask here is that, okay, this is the description of B. This is like an indirect, like an implicit description of B, where we do not say what equations W satisfy. We just say that it is a collection of all those W's for which I will be able to find out an L, so that together they satisfy some equation. The question is it possible to write this also as a kernel? Is it possible? If B full is given by a kernel representation, is it possible to obtain? Not just obtain, is it really true that B can be written as a kernel, and if so, can we find out this R tilde? Okay. So, that brings us to this question, that what sort of equations are we expecting involving W and L, and then what do we do in order to get equations involving only W. So, what sort of equations do we expect involving W and L? Well, we can have something like R psi W is equal to M psi L, right. This is a latent variable description. Sometimes it is also called an autoregressive moving average description, a terminology that comes from time series analysis. Yeah, mostly dealing with discrete systems, I mean sequences. You see, the kernel representation that we have been looking at, R xi w equal to 0, these are called autoregressive systems. Why are they called autoregressive systems? Just look at one typical difference equation like this. Yeah, in difference equation cases, like for example, suppose I have this polynomial sigma squared plus sigma plus alpha times sigma beta times 1 w equal to 0. Yeah, it looks like this, no, polynomial. This is of course discrete, right? A discrete system, discrete difference equation looks like this. It's a typical. So this w is coming from the kernel of this difference operator, right? Yeah, alpha beta of course are real numbers. Okay, now what does this mean really? It means the following. Remember, what is sigma of w evaluated at k? That is w k plus 1, right? This is just left shift. So then the difference equation that we have, sigma squared plus alpha sigma plus beta acting on w is equal to 0. This means it's identically 0. That means this evaluated at k is equal to 0 for all k. For all k in Z. Yeah. This then means that sigma squared w evaluated at k, that is w k plus 2, plus alpha times sigma times w evaluated at k, that is w at k, w at k plus 1, yeah, plus beta times w at k is equal to 0. Such a thing is called an autoregressive model. Why is it called an autoregressive model? This of course is for all k in Z, because if you draw the picture of the situation, what we have is, this is the time axis, this is an arbitrary point k, this is k plus 1, this is k plus 2. It says that whatever the value of the function is at this, then alpha times this and beta times this sum must add up to 0. There is a window looking back, it satisfies some linear combination going to 0. That is why it is called an autoregressive system. Yeah, it is a regression on this trajectory and its various shifts. That is why it is an autoregressive. Okay. Likewise, as I said, this is called an autoregressive moving average sequence. Why is it called an autoregressive moving average sequence? Because when you have R xi w equal to 0 means it is autoregressive. Here the autoregression part is there, but there is, together with that, there is also m xi l, where L is kind of assumed to be a free variable. Now look at this guy, what does this say? It says it's not equal to 0, but once again, if I go back to my time series kind of an analysis thing, suppose I have sigma squared plus alpha sigma plus beta like before w, this must be equal to, suppose this is sigma square plus gamma sigma plus delta acting on L. What does this mean? This means that when you have this, this is w k plus 2 plus alpha w k plus 1 plus beta w k, that is equal to L at k plus 2 plus gamma L at k plus 1 plus delta L at k. Treating L as a kind of a free variable, this means that if this is some L trajectory, this guy, autoregression would mean this is equal to 0, but now I am saying it is not an autoregression, but rather the value, this sum is equal to this moving window that acts on, that this window moves across this timeline, and each time whatever part of the trajectory L falls under this window, I take a linear combination of that, I take a sum of that. That is like a moving average. Yeah, that is why it is called an autoregressive moving average system. A special case of this, of course, is just moving average. That means when W is indeed equal to some m xi times L. There it really, the terminology really makes sense, that W is indeed a moving average of L. Indeed, you see in this case what will happen is Wk will be equal to, suppose this guy once again has the same structure, it is going to be L at k plus 2 plus gamma L at k plus 1 plus delta L at k, right. Yeah, these are the standard terminologies. For our purposes, we are going to use these terminologies. We will say, of course, when we have R xi W equal to 0, this is just a kernel representation. When we write R xi W equals m xi L, we're going to call this a latent variable representation. And the special case of this is when we have this, and there we are going to call this a image representation for obvious reasons, right, because we are going to call this an image representation, because you see, like earlier we used to write W belongs to kernel, here it means that W belongs to the image of the operator m xi, right. That is why it is called an image representation. The point that remains here once again is that if we have these kind of descriptions, is it possible to obtain the description of the behavior? Remember, the behavior is obtained from the full behavior through this logic. Yeah? This is the description of the behavior from the full behavior. In more sophisticated language, B is in fact the projection of the full behavior to the W part. This projection. The question is this projection a behavior, and is this given by a kernel representation? If it is given by a kernel representation, how to obtain that kernel representation? That is the question that we are asking. Okay? Okay. Great. How do we do that? This is where the idea of elimination comes into the picture. How do you eliminate variables? Eliminate latent variables. Yeah, that is what we want, right? Remember, in linear equations also, when you have linear equations, if you have multiple variables, if you want projection, you have to eliminate those variables, right? You have to eliminate various variables and obtain equations in terms of the other variables. You have been doing these things since your high school, I am sure. Remember, if you have simultaneous equations, a11 x1 plus a12 x2 equals b1, a21 x1 plus a22 x2 equals b2. How did you eliminate? I hope you remember that you did eliminate variables, right? Right? Like for example, you multiply this guy by you multiply this by a22, you multiply this by a12 and then subtract, no? And subtract. If you do that, then x2 goes away. That is the elimination of x2, and you have an equation given in terms of only x1, so you can solve for x1. But can we do the same thing when we have simultaneous equations, differential equations involving multiple variables? Like this. Can we do this elimination? And this is okay, this is done. We know how to handle these things. Can we eliminate L from these two equations? As an example of such elimination, remember your standard state space description, x dot equals ax plus bu, y equals cx plus du. This is a latent variable representation, believe me. Yeah, believe it or not, but this is indeed a latent variable representation. What are the latent variables? X, of course, the state variable. It does not show up in the input output description of the system. It is the input and the output that we are interested in, but the description is given in terms of x. Can we eliminate x? Yeah, we can indeed eliminate x. We can obtain this transfer function, but transfer function that relates u and y, right? But transfer functions is not what we are interested in. We are interested in a kernel representation. Once again, the differential equation that describes the system. Can we do that? The answer is yes, of course, but how do you do it? To get to the answer, we have to go back and we have to learn a very fundamental result called the fundamental principle, in fact, fundamental principle of algebraic analysis. What is that? Let me explain the fundamental principle, and then we will see a proof of that via another classic result called Smith canonical form. Okay? Right. So what is the fundamental principle of algebraic analysis? The question involves this basic curiosity. Okay, what is that? I want to solve for something like ax equal to b. Yeah, given a b, when is it guaranteed that an x would exist? But of course, our situation will be a little different because we will be dealing with differential equations. Once again, for discrete, it will be difference equations and same result will hold fundamental principle, but I will not do that explicitly here. I will give it to you as exercise problems. So suppose I have a xi x equals b. Now let me explain what these things are. This is the explanation. A xi, of course, is a polynomial matrix. Once again, let me assume that it's a size g cross q. It's a polynomial matrix, polynomial differential operator. B is a C infinity function of size g. This is known. This is known. This also is known. These are given to us. What is unknown is x. X also assumed a C infinity function of size q, but it is not known to us, unknown. We want to solve for this. We want to solve for this unknown x. When does a solution exist? The solution exists. The question is, when does a solution x exist? Yeah, you may immediately say that a solution exists if and only if b as a C infinity function belongs to the image of the operator a xi. Yeah, of course, trivial, no? What is the image? Everything that is there in there that can be written as a xi times some x, correct? This is in fact, so this is the collection of all C infinity r q. That's the image, no? This is defined as the image of this operator, which is nothing but the operator acting on all of C infinity. That's the image, right? So an x exists, of course, if and only if b is there in this set. So b must be there in the image. That's all right, but this is all what do I say? This is just mere retranslation of what we have been asking. It doesn't give us any way to get to the solution, get to the answer of this fundamental question, that does such a solution x exist? How do you check whether something is in the image? Let's say for linear equations, somebody gives me a matrix, a real matrix of size g cross q, yeah, and also somebody gives me a b which is in size g, yeah, which is of size g. Then how do you check whether whether B belongs to the image of A or not? I'm sure you know the answer. You look at A, you augment A with B, and then you do row operations and bring them in row reduced echelon form, and then you ask the question that whether rank of A is equal to rank of the augmented matrix or not, right? That's the condition, right? Isn't it? But here is the problem for us to carry out the same thing if we want to do this for this case, for the differential equation case. The problem here is that for the linear equations case, A and B both are of the same type. This is a real matrix, this is a real vector. So, I can simultaneously do this upper triangularization and stuff. But in the case of differential equations, this is a polynomial matrix, whereas this is a trajectory. Two different things, apples and oranges. How do you do this rank calculation? Doesn't really make sense. Yeah. So, unlike what we have been seeing so far, where things from linear algebra had some sort of an analogous thing happening in the case of differential equations as well, here it sort of falls apart. Here it doesn't work out. What to do in this case? Well, it turns out that although this doesn't work out, something from linear algebra will make sense even here. What is that? That is where the fundamental principle comes about. Right. Look at this A, xi, right? And find out an R xi such that this product is equal to 0. As a polynomial matrix, what is this R xi? R xi is a polynomial row vector. What is this size? 1 cross G, of course, right? Because there are G number of rows. So, you find out 1 cross G polynomial such that this is equal to 0. B is in the image of A xi if and only if for every R xi satisfying, for every R xi in R1 cross G xi satisfying R xi A xi is equal to 0, we must also have R xi acting on B is equal to 0. That is the condition of B being in the image. B is in the image if and only if every polynomial row vector that is kind of orthogonal to the columns of A xi, it must also kill B, it must annihilate B. But remember, whereas here this orthogonality is happening by just polynomial multiplication, here it is the differential operator. It is the operational meaning of this R xi operator on the trajectory B. Yeah, this is an analogous thing that happens for linear equations as well. Yeah, indeed, if you are asking for this question Ax equal to B and that augmented thing you have done, they having the same rank actually means that if you look at the orthogonal complement of the rows of A, they must also be orthogonal to B. Yeah, indeed, when A has been brought to, let us say, a row reduced echelon form kind of a thing, it has been brought into a row reduced echelon form kind of a thing. This is full row rank, right? And the remaining things must be 0. What is the solvability condition for this? This is A. When you augment this with B, this means that you have done the same row operations on B, and B must have this form. Then and only then A and A augmented with B will have the same rank. But the meaning of this, yeah, indeed there is a solution. If and only if this is what happens. The solution doesn't exist if there is some star appearing here, some non-zero entry appearing here, which changes the rank of A augmented with B from the rank of A. and there no solution exists because essentially because we are having absurd equations 0 not equal to 0 because of this part. But now if you ask yourselves what is the meaning of this in terms of the orthogonal complement kind of things, you see this means that anything that kills these rows must also kill this guy, this B. Yeah, indeed, what kills this guy? The only thing that kills this guy is the first few things, namely these many things should be 0. The remaining part can be anything. And B having no zeros in this part, that's the same as saying that whenever we have 0 for the first few things and arbitrary things remaining, that kills B only when we have zeros guaranteed in the remaining part. Yeah, think about this. Or if you want more sophisticated language, what this means is we are interested in whether B is in the image of A, but that's the same as saying that B should be killed by the vectors that are orthogonal to A, which means B must be in the double perp. Yeah, listen carefully. B must be killed by everything that kills the image of kills the columns of A. Yeah, so that means let me rewrite it so that you understand it well. This is the same as saying, okay, this is the same as saying B in the, this is if and only if B is in the image of double perp, because in linear algebra subspaces double perp is the same space. This is if and only if B is orthogonal to the orthogonal complement of A. That's the same as saying R transpose B is equal to 0 for all transpose R transpose such that R transpose A is equal to 0. Right? So I hope you understand what is the meaning of this, and this is the fundamental principle. This right now what I have stated, this is the fundamental principle. If you have done linear algebra, then just think about this, the linear algebraic analog will be very clear to you. But how do you prove the same thing, this fantastic thing for differential equations is something that we'll see in the next lecture, right? Till then, take care of yourselves. Bye.